How are you doing today? Hope you are doing well. I am doing swimmingly. Okay, so last time we talked about circuits. This time, we're going to talk about circuits some more. Specifically, we're going to go over an example of Kirchhoff's voltage law and Kirchhoff's current law. This is kind of the example, pretty much the simplest example you can do, more or less, with using Kirchhoff's voltage law and Kirchhoff's current law. And if you do any sort of engineering, this maybe not this this specific problem will come up at some point in life, and it's good to know how to do it, and good to know how to do it in an efficient manner so you can get it done quickly and get the correct answers, which is also important. Okay, so we're given a circuit like so, and the question then is, what is the power at resistor 3? So power at that guy right there. Then we'll also say, what is the voltage at point A, where this is point A right here. And then we'll say current through, let's see, it's through this way, and we'll call that R2, through R2. There's multiple 2 ohm resistors, so you have to be a little bit more specific. This guy will be R3. And so what this is more or less saying is solve for everything. So keeping that in mind, the way we start this one out is by doing loops using Kirchhoff's voltage law. So, as remembered before, the idea of called Kirchhoff's voltage law is if you have any loop, closed loop, then the voltages, and if you start at the beginning and then come back to the end at the same place, then the voltages will be zero. The voltage gains will equal the voltage losses, and therefore you'll be left with no change, which kind of makes sense because we're going to start here with our first loop, and if we went around and we had a non-zero voltage here, then that would say that there's a difference in potential energy there, and you'd have basically electrons flowing into themselves, and that just doesn't work right. So I'm going to start off. We're going to do 2 loops. We'll do one loop like this, and then we have another battery over here, which is what makes it, the second battery is what makes it really difficult to just do equivalent resistors and summarize everything down into one equivalent resistor. So we'll do one loop like this and another loop like that. You can choose the loops however you like. But when I choose loops, I try and choose the loops in the way that I think the currents are actually moving. And we're still using the convention that a current is a positive charge moving in the positive direction, as opposed to reality where it's electrons moving in the negative direction. So if you think of these as pumps and the wires as pipes, then you have a pump here, you have a slightly bigger pump here, you have 4 ohms here, but you have 5 ohms there, and so they're probably both going to push water up this direction, and then down through the middle, and then back to the suction inlet side of the pump, or the negative side of the battery. So if we choose loops like this, then that's probably actually the direction of the current. One thing that might happen is you choose incorrectly, which is fine, and then you get a negative value for one of the currents. Well, if you have a negative value for the current, then that just means that arbitrary arrow that you drew for the loop was in the wrong direction, which is, you just reverse it and you're fine. So I'm going to start over here with loop 1, and I'm going to write out our Kirchhoff's voltage law. So start here, we go through the battery, that's going to be 9 volts. And then we're going to have a voltage drop across the 4 ohm resistor. I am going to say we're going to have 3 separate currents or flows. I'm going to call this I1, I'll call this I2. Not to be confused with the I going through the 2 ohm resistor. I'm going to call this I3. And you can see how the loops are situated, are chosen in such a way that they would go through the loops. They would follow the arrows. Okay. And for this ohm resistor, we'd have voltage across the 4 ohm resistor. And nope, I'm not going to do it that way. So that's true, but I'm going to use Ohm's law. So we have Ohm's law, which is I equals, I'm going to say delta V over R, but it's normally just written V over R, which implies that voltage equals IR. And since it's a voltage drop, we want it to be negative. And so for that specific resistor, it's going to be I4, and then I'm going to write 4 for the 4 ohms. We then come around with the loop, 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 loop. Then we get to I2. Now the problem is we're actually going to have multiple I2s here. So some's going to go this way, and some is going to go that way. So what I'm going to do, what I probably should have done to start with, is I'm going to redraw this and combine these 2 resistors and these 2 resistors. So I'm going to redraw it as battery 4 ohm, and then I'm going to do a little sidebar here. So to find the equivalent resistors of the 4 and 2 in parallel, we'll do 1/4 plus 1/2 equals 1 over R equivalent. Adding these up, we have 1/4 plus 2/4 equals 3/4, which equals 1 over R equivalent. So R equivalent equals 4/3. I'm going to draw this set of resistors over here, which will be 2 plus 3, which will be 5. And then we'll still have the battery. And then it comes down. Okay. So this is the diagram we're going to work with. And this right here will be I1. This right here will be I3. And then down through the middle will be I2. You can choose any way you'd like. I just like to go from left to right. Visually more appealing. Okay. And we'll do the 9 volt. I think this one was 9 volt, and this one was 12 volt. Okay. Oop. Transport my voltage law. Okay, so now, did I say I4? This should be I1. Yeah. Oop. Perfect. So we have I1 coming through here, then we'll have I2 going through 4/3, back to purple, minus, let's do I2 times 4/3, and then back to the battery, so back to our starting point here, which is 0. So the batteries will raise the voltage, but the resistors will drop the voltage. There'll be a voltage drop across the resistor. Which kind of makes sense. You can't get a whole bunch of resistors, put them in your car, and make it go. Okay, so now we're going to the other loop, which starts here, goes around, and then comes back. So first thing we'll do is we'll go through the battery. We have a rise in voltage. Then we'll have I3, because this is I3 in this loop here. So we'll have I3 times 5 minus I2 times 4/3. That will equal 0. So now we have 2 equations and 3 unknowns. So we need 1 additional equation. Remember from what's it, advanced algebra? Advanced algebra, you need the same number of unknowns as equations. So we could try and do another loop. We could do a loop kind of like this, and that'd probably work. But one of the easiest equations to get then is Kirchhoff's current law. And we're going to do it right. Let's see what color we have. Ooh, red. Right there. And so we know that all the currents coming in, I1 plus I3 equals I2. Because all the inputs will have to equal all the outputs. Think of it as water going through a pipe. All the water that comes in is going to be all the water that goes out. Ideally. Unless you're getting denser water. What's it? Incompressible fluid. Okay. So I'm going to rewrite that slightly as I1 minus I2 plus I3 equals 0. All right, so now I have these equations that I need to solve. And I am going to rewrite them in a slightly different format so it'll be easier for us to solve them. Traditionally, you probably remember advanced algebra. You take one variable, you solve for like I1, you plug that into the next equation, you then solve that for I2, then you plug that into the next equation, and it all kind of works out. That is long and tedious and prone to error. So you want a way that's less error prone. So I'm going to rewrite this I'm going to rewrite the first one. Blue. Teal. So I'm going to rewrite that as 4I1 plus 4/3 I2 plus 0 I3 equals 9. So I moved the 9 volts over, and nope, I moved the I's over. And so 9 volts is on this side. Yep. All right, then I'll do the same for the second equation. So I'll have 0 I1 plus 4/3 I2 plus 5 I3 equals 12. And then we have 1 I1 minus 1 I2 plus 1 I3 equals 0. Okay. And these are going to be our equations that we solve. Not sure how much exposure you've had to linear algebra or matrix theory yet, but this is the real value of having your TI-83. So grabbing our calculators, kapow. Did it turn off? On. RAM cleared. Okay. Come back, calculator. There you go. So to do this, where is matrix? Matrix! There it is. Second, matrix. Let's go, we'll use matrix alpha, so we'll edit. And then this is going to be a 3x4 matrix. The way that I remember it is, I don't actually like Royal Crown Cola, but if I did enjoy a cola, it would be Royal Crown Cola. And the reason that is, it has nothing to do with the taste. It's a generic cola. Delicious generic cola, just in case Royal Crown Cola is listening. And it's because the format is rows by columns. So we have 3 rows, 4 columns. So rows by columns, RC, 3x4. So 3x4. And enter. And the way we set it up, this will be the first column, second column, third column, etc. By etc. I mean fourth column. 4 divided by 3, enter. 0, enter. 9, enter. 0, enter. 4 divided by 3, enter. 5, enter. 12, enter. 1, enter. -1. Make sure to do the negative and not the minus. 1, enter. 0, enter. Okay, so now we have our matrix, second quit, second matrix, bam, have the matrix A is right there, see, right there. We'll do some math on the matrix, and what we want is row reduced echelon form, right here, row reduced echelon form, RREF. And we're going to do that on matrix A, and then I'll do a little close parentheses, probably not necessary, but, and what it does is it does the same math that you would do through substitution and getting it, I guess, reduced down. And so what it does is it created a equivalent matrix for us, 1 0 0 0 1 0 0 0 1, where this is implied I1 implied I2. That's a terrible 2. I feel slightly ashamed of that 2. There we go. I3. And then it gave us another row. Click. Oh, it's right there. 1.28. So 2.91. And the last one, 1.63. 1.63. So what this is telling us is our currents, I1, I2, I1, I2, and I3. I1 is 1.28. I3 is 1.63. And then I2, which should be the sum of the two, which it is by this equation. And if you look at these, you're like, yeah, 1.3 plus 1.6 is like 2.9. So I'm like, okay, that's at least plausible. So let's see. Now that we basically solved for all the currents in the system, more or less, because I2 branches off here, and you could be like, well, I4 and I5. We could. We're not going to go for that right now. So you should read what they're looking for before you start the problem. That way you can know if you have to do a lot of work or if there's some shortcut. So in this one, there really wasn't a shortcut. So you solve for pretty much everything important. So they want power at R3. So the power at R3, I'm going to rewrite. Can I just copy and paste? Aha. I should probably copy it, that way I don't lose it. There we go. So convenient. That is very convenient. But I want it a little bit slightly over to the right. There we go. All math should be done on computers. All right. I2, I3. Okay. So power is I squared R. That's where it comes for a resistor. It's called I squared R losses. I squared R. Alternatively, you could say use Ohm's law and say that I equals V over R. And so you could also write it as I times V over R times R cancels equals I times V. You can also write it as V squared over R, where you then replace the last current with the voltage. And these are all fairly equivalent, and they would all work the same for resistors. But physically speaking, the equation that actually best represents reality for a resistor is I squared R. But at some point in life, it might be more convenient to do substitutions and use one of the other ones. So that was a little bit more tangential than I meant. But yes, if you're given just the voltage and resistance, you can use V squared R to find the power. Another way that I remember that the equation for power for electrical components is, I remember that centripetal acceleration equals power electrical. And you thought, what? Is that even true? Well, it's a gross conceptual error, and the conceptual error is so terribly gross that the mnemonic sticks in my head. Straight mnemonic, no actual fact. So centripetal acceleration is velocity squared over radius, which kind of sort of looks like voltage squared over resistance. And complete coincidence that they have similar symbols, but it's such a terrible misunderstanding of physics that it's hard to forget. And so if you're ever like, wow, what's electrical power? Be like, okay, centripetal acceleration, there's a V squared, and there's a divided by R. And if you have trouble remembering what centripetal acceleration is, the more ties you can make mentally, the less likely it is you'll just blank out and forget everything in life. Okay, back to focusing. Whoop. Erase this. Clickety-clack. We got an I squared R. Power at 3 equals I squared R. We know that the current at 3 is 1.63. We'll square that and multiply it by 3, because it's a 3 ohm resistor, which is go over to Wolfram. I know I have a calculator. I just don't like that calculator. I'm more of a Casio person myself. 1.63 squared times 3. I'm going to call that 7.97. 7.97. 7.97 watts, or joules per second. Okay, and that was the first part. Next question is the voltage at point A. Okay, so remember when we did Kirchhoff's voltage law, where you basically do a loop and you look at the voltage drop at each point? Well, we can do the same thing but not do a complete loop. Now, if we don't do a complete loop, it's not going to equal 0, but that's okay because we don't want the voltage, we don't expect the voltage at A to equal 0. If it did, we'd have serious troubles. So I'm going to start at this point again and then go all the way up to A. And we can do that now because we actually know what current 1 is. And so we can, before when we had this mysterious current 1, we were kind of stuck and had to solve the whole system. Well, now that we know what current 1 is, we can actually find out what the voltage at point A is. So we'll start with, and I'll write this way. So voltage at battery minus voltage at the 4 ohm resistor equals voltage at point A. So this would be 9 minus I1, because that's current 1 is what's passing through resistor 4, times 4 equals voltage A. Okay. So 1.28, 9 minus 1.28 times 4. And at this point, if we get a negative number, we have made a terrible, terrible mistake. 1.28. Okay. You guys got this? 1.28. 1.28. 1.28 times 4, 9 minus 3.88. Okay. Go back. It's a 3.88, right? 3.88. Okay. 3.88 volts. Because this is volts, and then by Ohm's law, V equals IR. So that is also volts. So I'm going to write that voltage at point A equals 3.88 volts. Good for us. I'm going to take a quick victory drink. Crystal Light, you are my one true love. Okay, so now we want to find the current through R2 right here. And this is a little bit tricky because we know what I2 is. I2 is like what, 2.91? But some of the current is going to go to the left. And some of it's going to go to the right. And so we have 2.91, and we need to figure out how much goes to one side and how much goes to the other side. So just intuitively looking at this, you could think of this as doors to a coliseum where one door is harder to get into than the other, but they're still in parallel. And so it's twice as difficult for current to go through this one as it is to go through the two, because there's only 2 ohms of resistance to get through this side, while there's 4 ohms of resistance to get through the other side. So if you think about it, there should be twice as much current going through this side as the other side. So I would expect an answer where it's say 2/3 of the current goes through this side and 1/3 goes through that side. And so I'm going to guess 2/3 times 2.91 is like what, 1.9? 1.93 will go through this side, and whatever's left will go through the other side. Was it 0.98? But that's not the way I'm going to solve it. So that you can do an actual ratio there, and we probably will in future problems. But the way that I prefer to solve this one is we have Ohm's law, which is current equals delta V over R. We just figured out what the voltage is at point A. That's 3.88. 3.88. And we know the voltage at this side down here. So the voltage here is the same as the voltage here, which is the same as the voltage here, because they're all connected by a wire. If you have a wire connecting 2 points, it's going to be a conductor, and so the voltage will be the same, which is the same as the voltage here, which is the same as the voltage here. And one of the assumptions of the batteries is this battery has a difference of 12, so it'll be 0 there, 12 there. This battery has 9 volts, so it'll be 0 at the bottom, 9 at the top. This is part of our assumptions. And since these are, and the reason you know that these will both be 0 is they are connected by a wire, so they have to be at the same potential. And you could be like, well, as we discussed earlier, it really could be that, well, this is at 3, that's at 15, this is at 3, that's at 12, as long as the difference is the same as the battery. But for the ease of writing this out, we're just going to call the minimum voltage we have on the circuit 0. It just makes the calculations easier. Okay, so we have 3.88 and 0, and then we have a resistance of 2. So we're going to have a 3.88 minus 0 over 2. 3.88 divided by 2. I'm just going to leave that up there instead of rewriting 3.88 divided by 2. We have 1.94. So I2 equals 1.94. Not very good at those 4s. Back to pen. 4 amps. Okay. And that is pretty much everything that you would be asked to solve on a problem like this. To backtrack slightly. Boom, 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 boom. Yes. So the current passing through, we were correct. Most of it goes through this 2 ohm resistor, and then the rest would then go through the 4 ohm, and then the two currents would recombine, and it'd be back to the original 2.91 amps. Reviewing how we did this, so we had 2 batteries, which you can combine batteries if you have a battery like this, which is 3 volts and is connected in series to a battery like this, which is 4 volts. You can combine those into a 7 volt battery. But if you have, if you have them opposite directions, you could, let's see, this was 3 volts, this was 4 volts. You could combine that into one battery pointing downwards as 1 volt. But when you have batteries set up like this, it's not that easy. And you really, these aren't in series and they aren't really in parallel. And so, well, I guess they are in parallel. But then they kind of, this is not an easy way of simplifying this battery setup. So we had to use Kirchhoff's voltage law. So we drew a loop. We weren't really sure how to draw the loop, but we kind of used our spider senses intuition to go along the direction that we thought was the current. If for some reason like I2 had been like negative and we drew the arrow down for I2, then it would have just been the opposite direction. So if we had assumed that I2 went in this direction, then we would have gotten a negative number for amperage, which would have then told us that the amps was actually down. One thing to note though is when we drew the battery, when the current went through the battery this direction, we saw a rise in voltage. And then when we went through the battery in the same direction as the current, we saw a drop in voltage. That was our negative IR. If for some reason we did our loop and we went this direction with the current assumed being that direction, then that'd actually be a rise. We'd add IR to the voltage drop for the loop. So generally convenient and simple if you try and do everything in the direction of the current, and then you add the batteries as you go through them in the positive direction from negative to positive, and you subtract the resistors when you go through the resistors in the same direction as the current flow. Through our loops, we wrote out a couple of equations, one for each loop that we had. I realized partway through that it was going to be easier if we simplified the diagram. So we combined these 2 parallel and combined these 2 series resistors. Put together our system of equations. We used our calculator to create a matrix that was row by columns, where there was one more column than there was row. Put the voltages on one side, equals, and then use the calculator to solve for RREF, row reduced echelon form. And the far right column is what gave us the answers to our currents. And be careful too, if you left these equal to 0, then yes, you move the voltages over to one side. This is the constant over here that things equal to. And then we wrote in our currents, and then we used the current flowing through the resistor for the I squared R, which gives us the power delivered by the resistor. We then looked at the voltage drop across one resistor, went from 9 volts to 3.88. Yep, went from 9 volts to 3.88, which gave us a voltage at A, which is one of the things that was asked for. And then we used the voltage at A and looked at the voltage at the other side of the resistor to find out how much current was flowing through that resistor. We also could have done it by just looking at a ratio of the resistance of those resistors. That would have also given us the same answer. And that is how you solve this kind of problem. So we'll go over a few more circuits problems next time, give you kind of an idea of the sort of things you'll see on an AP exam. So appreciate you listening, and I will see you guys next time.